Ready? Okay, so just because for the folks who aren't going to be on the call, we can make sure that they get all of the wit and wisdom that we all collectively distribute to each other here during the call. Yeah, when we were just talking before, Fahim, right? That's your first name? Yeah. So does anybody else have any questions specifically you want to touch on before I get into some of the, I thought I'd do a design problem here, a real world design, as opposed to working through one of those exercises. We can touch on the exercises as you get deeper into it and start going, I don't know how to do maximum string calculations or minimum string calculations or, things like that, battery sizing. But for right now, I kind of wanted to pull it all together and start doing some real world examples. So anybody have a question before I jump in on that? All right. I'm going to jump into sharing the screen. So I may be kind of cumbersome here. The first one I was going to do is got to go into my emails. All right. Hopefully you're seeing here. Oops, I was just looking at an email there. I was going to go down here to Albert. Is Albert on the call? Albert, are you on here? I see you're there. You're just muted. Okay, so Albert, hopefully you're there. I'm going to, before I do this, Albert, if you could unmute yourself and just let me know, is it okay to share your address and the like with everybody here? Albert? I see you unmuted, but I'm not hearing you. Could you just give me a thumbs up if it's okay? I just don't want to show pictures of your house and give everybody your address if you're in the Federal Witness Protection Program or something like that.
Yeah. Okay.
You're okay? Okay, now I can
I'm
hear
okay with that. But can you hear me now?
Yeah, I can hear you.
Okay.
Okay, can you see the screen then? Am I showing your electric bill there to you?
You are.
Okay, so this is a typical electric bill. You use the illuminating company.
Yeah. Hey,
I'm not quite sure who that is, but normally with an electric bill, it's going to show all of the usage for the last year, month by month. So when you use one of these online programs, you'll want to collect up that data and plug it in. And then it looks like your average monthly use is about 520 kilowatt hours per month. For an annual use, I'm going to make a couple of notes here of 6237, 520 kilowatt hours per month. So that is, well, if you'll remember from one of the previous chapters, the average suburban home uses 900 and some change. So this is going to be just over 50% of a typical residential system. So we've got the information we need here. We also needed the address. So I'll take your address here. And the first step that I go through is now, I think I've got to stop share and then share again to go in to my program. All right, so if I go in here and go to, all right, come on. The menu bar is up here trying to block me from going to the thing I want to do. I can move it. There we go. All right, I'm going into PV Sketch here. So you can use any of these kind of automated programs, but this is just a good one if you want to practice. You can do up to 5 a month. They charge you $4 per design if you want to go through the full thing. I'm not going to go through the full thing on this because I don't want to spend $4. But so you'll plug in the address. It's going to ask you to verify, is that the one? Then we can start a project, and it should bring in an aerial view of your home. Does that look like your home there, Albert?
It
Albert?
does. The red
Okay.
dot is right on it.
All right, on it. Yes, you live in one of those where you've got to know the number of your house in order to find it.
Yeah.
So, all right. So we're going to come down on your house. It looks like now these aerial views typically will give you a southern. South is at the bottom. So, did you think about where you wanted to put the solar array? Do you want to do a ground mounted or on the roof, or how do you want to do this?
I think it has to be on the roof because of the HOA.
Okay, that makes sense. And is this a little carport or garage in the front there?
Yeah, that's half of the garage, right?
Okay, so is that the location, or would you go all the way up on top of the roof, do you think?
I think you'd go all the way on the top.
Okay,
think.
so I'm going to then take this tool and I'll outline. It looks like the shadows are a little bit tough to see. But does this look like, is this a flat surface basically that I've just outlined there?
It is. It is.
Okay. So in this case, I've defined.
Actually, I think you cut part of the part that juts out a little bit. That bottom right corner is actually on top of a non-flat part. That should be pulled in a little bit.
Oh, okay. Down here where.
Yeah, should pull that.
Or up.
No, you can't.
Well, I think you might be able to. I think I've just got to get out of that tool and
there we go. That's it.
Something like that.
Yeah.
All right. So now you can see the arrow is pointing you off west. So I've got to make some changes over here to readjust the azimuth here. It's showing me it really just does this based on which corner I started at. So I guess if you practice with it, you'll avoid that problem. But it's showing it at 256. So if we deduct 90 from that, I think we're going to be at, what is that?
160.
166.
Yep.
Let's try that. Yeah. So the arrow looks like it's going the right way at this point. So your azimuth is going to be 166. Do you have a sense of the slope of the roof? About 20?
None whatsoever. Take a guess. Standard.
Yeah, standard's 20 degrees. You could take your smartphone and measure it, stick your hand out a window or something and measure it if you want. Then the height, is this 2 stories?
2, right? Yep.
Okay. So it might be, let's say, 20 feet high. You don't have to be that exact. And because it's residential, we're going to be a 36-inch setback. Really, so now it's defined what the area where the solar array could be located. All right. On there. Now, this is something you can play with a little bit because the eave and the top, we could go to 18 inches. In fact, that's probably a better number because you'll see we'll adjust in it. Because at the peak of the roof, you could have 18 inches on one side and 18 inches on the other side, and that will count. And down at the eave, it doesn't really matter. There's no setback required by code, but you typically want to put it back 16 inches. So, all right, now I'm going to go into the system and I'm going to say, all right, I'm just going to randomly pick some panels. I'm going to say a Canadian Solar 330 watt panel because I'm going to use some microinverters on this. So I'll use the N-phase microinverter and we'll use the latest version, which is the IQ8. So we'll go with the state-of-the-art stuff. And then you'll have to decide, is it going to be portrait or landscape? And do your rafters, I assume your rafters go from the eave to the peak. Is that right?
Uh,
Like trusses in there where they're built out, where the rafter itself, the support rafter, goes from the eave to the peak. So they would be running north south instead of east west.
I think so. Yes.
It would
I
make
haven't
sense.
looked up there in a while, but I'm pretty sure they do.
Yeah, just based on the way the house looks like it's built.
Yep.
So if you do that, then of course, if the rafters are going north south, then the rails are going to go east west, which means then the panels are going to go north south on the rails, because you always bisect the lengthwise, the longer portion of the panel. So in that case, the panels are going to be portrait.
Portrait.
Yes. So they're going to be portrait. So now I've defined what's over here. System losses, I'm going to change that to 8%, because that's the number I like to use with microinverters, because they're a little more efficient. So I've changed that to 8%. Now you hit the button that says generate design, and it's just going to automatically take the modules that I've selected and fit it within the area that is available. So in this case, it's saying that within that section of roof, given what I've defined, I can put a 4.29 kW array or 13 panels. All right. That's going to generate about little less than 6,000 kilowatt hours per year, 5914. Well, your usage shows 62.37. So you're pretty good there. In fact, I'll bet you if I go to a slightly larger solar panel, let's see what happens if I go to the 335. Yeah, that kicked it up just over 6,000. So we go to a slightly larger solar panel. So I would say that this, if I were designing your house, rather than trying to put them in another area as well, I'd be kind of happy with it as it is. Now, the question that I would ask you specifically, given just the nature of this house, does your homeowners association have any restrictions on panels being seen from the road?
I don't know.
Yeah, you might want to check that. Is this in Ohio?
It is.
Yeah, because I think that if they do, they're illegal. So
that's what I was thinking as well.
Yeah, I think there's legislation that prohibits them from unduly restricting you on that. But that doesn't mean they're not going to do it, so you might want to check.
Right.
Sometimes, homeowners associations can be a nightmare. So hopefully yours is well behaved with adults running it, but you never know.
So the question I had is, there's that other spot above the garage that could be used.
Uh-huh.
Now our bedroom window looks over that part of the roof. Would that be a good idea to put stuff there, or?
You could. I can just see if I put in another array here.
Guessing it would be easier to get to and access. And
Sure. If we use the same panels and the same kind of layout, I'm not sure. Let's just see. Oh, it's just saying because of the setbacks, it looks like I could only fit one row of panels there. So you wouldn't be able to do it just by itself.
Okay.
You'd have to go with in two different sections. So my guess is you're probably better off just up there in that area. So I'll delete this one.
And that's not going to cover everything, all the electricity I use in a year.
Right. It's going to get you to about 95%, I think.
So if we did end up getting an electric car, it's not going to charge it.
Probably not. Probably
Right.
not. Unless you add, then at that point, you might want to think about adding on your garage roof.
Yep. Okay.
So that's something that you might want to do in the planning. Now, if I cheat over into the, well, I don't think I can, just looking at,
No.
I might be able to. I might be able to fit one more panel in here. Let's say that if I cheat over and ask it to generate just by knowing that I can shift it to the left a little bit, then I'm up to a little more than you're consuming, 64, 66. So that might be something we can do. I just have to look and do the measurements on site. But but this gives you a rough idea of what some of the issues are. All right, so the numbers I want to pull from this, let's just assume we can do 14 panels. We've got a 4.69 kW array, and the azimuth is 166. The altitude is 20, and I put it at an 8% D rate. Okay, the reason I'm writing these down is now I want to jump over to PV watts. Did that transition seamlessly there to PV watts? Okay, so I'm going to plug in your address here, and it's going to find your location. And now it's going to ask, all right, what size array? Well, we just wrote down that it's 4.69. Not 469, 4.69. And we're going to say that it's standard panels, fixed open rack. I said it was an 8% D rate, tilt of 20, but the azimuth is 166. And then I think under advanced parameters, you can put in like the AC to DC ratio, the inverter efficiency. Now, I do know that the microinverters there are about 98% efficient. I usually don't mess with these things in there very much, but then it's going to jump in and it's going to say, oh, well, based on this, with the PV watts, it's telling me that it's going to generate 6470. So if I compare that, this said 6466. So basically they're right on target with each other. Your hours of insolation at that at that azimuth and that angle are 4.36. So this is how you would get that from PV watts. And if you're doing a design for somebody else, you can print out or save this as a PDF, and this will show them how much energy is being produced. Now, one of the things PV Sketch will do is it'll match up your production. Because if you look at the amount of solar radiation, in January, you've only got 2.04 hours of insolation. In December, you've only got 1.86. But you get into July, you're at 6.53. So you're going to be generating a lot more power, pretty much more than 3 times as much energy in the summertime as you will in the wintertime, just because of the amount of hours of solar radiation that you're going to be getting, or the insolation. So this is just showing you that in AC kilowatt hours, you're going to see about 731 there and 250 down here. So anyway, it matches it up with your consumption.
So Jay, it actually puts out more energy when they're colder, correct?
Yes. But
so does this take temperature into account?
Yes, it does. With well, it does with the output here in the energy area. But it doesn't with this first column. It's just taking it and saying, okay, because the days are longer, there's less cloud cover, all this other stuff. This is historically how much energy generation you're going to see, how much solar radiation. Then if you factor in heat and cold, it's going to modify it somewhat. And that's adjusted over there. Now, an interesting article I was reading is that because all of this is based on historical data and the climate is changing so dramatically, we're finding in some parts of the country, this historical data is no longer accurate. So you have to sort of take that into account to determine, in the article was specifically geared towards California installers because that's where a lot of the activity has taken place. And they were saying you better essentially derate for climate change because you may find you're over predicting by about 8%. Whereas if you come to the Midwest, we're going to benefit from the climate change. So the places that have traditionally been good for solar, like the Desert Southwest and California, climate change is adversely affecting them, whereas places like Cleveland, it's helping. So, we'll see if that comes up in reality, but that's what they claim. All right.
Jay, when you see that big of a difference with the hours of installation, would you consider doing the winter bias to help balance it out, or no?
Well, again, there's no reason to, except if your utility company will not do an annualized true up. Because, okay, you're building up a reserve in the summer, but you're using it up in the winter. That's traditionally been the way it works. And so it's been when you're doing a grid tied system, it makes no difference. When you're doing a standalone system, it certainly makes a difference. And there's a whole different process where you take your usage versus, the production, and you figure out your optimal month, and then you base the system on that. That said, net metering laws are changing. So it may be that this becomes something you do in the future because the utilities are paying wholesale for power. So if you're overproducing in the summertime, but only getting paid 3 cents a kilowatt hour, underproducing in the wintertime and paying 17 cents a kilowatt hour, well, then maybe you'll want to make that adjustment. But since this is a rooftop system, I can't adjust the angle. I can't make it a winter bias or a summer bias. It just is what it is. So now if it were a ground mounted system, I could do that. I could make the adjustment. But rooftop, you don't want to put it at an angle as in relationship to the roof. You don't want the back of the array being higher than the front of the array. You want it to be parallel with the roof surface for several reasons. One is, of course, that's the way racking systems are built or designed. Secondly, it looks like hell if you do it. And thirdly, you're really setting it up to get caught by the wind and rip itself off of your roof. So don't do it. It's bad. It's bad on many levels. But on the ground, no problem. Just set the array at whatever you want to set it at. But as was mentioned, we may have a restriction by the homeowners association here of putting things on the ground, which is silly, but that's what they do. So, because it seems to me you could tuck a solar array back here at the back end of your property and nobody's going to see it.
Mm-hmm.
But they may or may not allow for that. So,
right. So Jay, you also mentioned wind. It seems like over the last few years, it's gotten a lot more dramatic.
Yeah.
And is that a problem?
Yes and no. The racking systems, they're typically warranted. And when you use their design element, when you just use, for example, Iron Ridge, which is a popular racking system, if you go into design using their system, it's going to tell you what the classifications are, the wind and the snow load and all of those things based on your zip code. So you're just simply going to plug in your zip code and the engineering documents are going to come out that tell you what that system is rated for. Let me see.
And those parameters are adjusted for more recent activity?
Well, that's the thing that you would hope, but I can't tell you that for certain. But they're warranting it based on that. So if they don't adjust, that'd be problematic to them. Is this mounting system report showing up on your screen?
No.
No. Okay, I'll stop sharing and then I'll go back in because I didn't know if it would show up that way. I've got too many things open. I've got to figure out where is let's see what happens here. Okay, there we go. Are you seeing an Iron Ridge document here?
I'm
Still
not.
Okay.
I'm seeing the list of documents, but not the Iron Ridge one.
Okay. All right. Let's try and do this again, showing you my lack of skill with Zoom. Oh, there it is. Yeah. All right. Okay, so here should be the Iron Ridge report that I'm doing for our offices here. And this is the kind of report that you can get from pretty much any manufacturer. So I plugged it in and put in the parameters, just the zip code. It spits out and it's telling me it's rated for 105 miles per hour wind speed, 20 pounds per square foot snow load, wind exposure category B, how many yards of concrete. But what's really helpful is as you go down through this, it's going to start showing what the spans are. So here between the vertical piers, I can go 18 foot, 8 inches with a 2 foot, 1 inch cantilever, which is basically how far it extends beyond the pier, the vertical pier. This is a ground mounted system, by the way. And then it shows, what kind of concrete requirements are here for the engineering for a side view. It shows all the little bits. And you can bring something like this down to your planning department. And these things are pre-engineered. So if your planning department has an issue with it, Iron Ridge will they give you a phone number, have the planning department call up, they'll talk to their professional engineers, and the professional engineers will walk it through. So all of these, you can even get printouts of engineer stamped documents if you need them. So that's one advantage of using a system like that. And pretty much all the manufacturers will do this. As opposed to you just writing it out saying, I thought it was a good idea, try and convince the planning officer, the code officials, that you thought your thing was a good idea. And it's a lot more convincing if you say, here's 17 professional engineers who will talk to you until you're blue in the face. And it's been installed in 10,000 different places and not nary a problem or whatever. So that's kind of the racking system, the structural system. That's kind of what they're going to worry about. Then let's see. So we've got your array size. Let's just do a one-line diagram here of what we're talking about now. So this is Albert's system. It's going to be a roof-mounted system. We've said, how many panels were in your array? Was it 14? Is that right?
There are 14, yeah.
14 panels. I said that these panels were 335 watt. And I know that the IQ8 generates 300 watt. So if we wanted to know what the inverter to load ratio is, we would just simply take 335 divided by 300, and you see it's about 1.1 and some change. That's the clipping aspect of all of this. That's your inverter to load ratio. If I want to know how much in amps each of these are going to be generating, well, the output is 240 volts. So the inverter generates 300 watts maximum, 240 volt. So what is our amps? Since watts equals amps times volts, it's 1 point something.
Yeah.
1.25. Is that right? Somebody with a calculator?
Yes, 1.25.
Yeah. Okay. So each panel is going to generate 1.25 amps. Now, if you go into the spec sheet, now this is kind of the easy way of doing your solar string calculations, because these are generating AC, so there are no strings. You know, everything is connected in proprietary parallel connection cable. So when I hook up 14 panels, the voltage remains the same. It's always going to be 240 volts, but the amps will increase for every panel I hook up. I can look on my IQ8 spec sheet, and it will tell me how many IQ8s I can hook up in parallel before I've exceeded the capacity of the proprietary cable that they provide. I'm not quite sure how many that is. It seems to me it's 16. I'd have to look it up, but I don't want to get out of this. So you'd look it up, and let's say it's 16. All right, well, we're doing 14 panels, so that's going to be fine. Well, 1.25 amps times 14 panels is going to give me how many amps?
17.5.
17.5 amps. So that's the actual output from the panels maximum. What do we do with wire size? Times 1.25, right? That's the NEC safety margin with all sizing of wire. So what's 17.5 amps times 1.25?
2187.
21.87. We'd look up in our table, and I think what you're going to find is 10 gauge wire, right? Is 12 gauge wire 25 amps in the first column?
12 gauge should be 25.
Yeah, so it could be 12 gauge wire, right? 12 AWG. And
Now,
that's
I've got
what
a
the,
question for you.
what's
Sorry.
that? Oh, that was,
why would we not multiply this again by 1.25 for the safety factor? Like again.
again, you mean the solar safety margin?
Yes, sir.
Yeah, it's because in this array, you only do that until you hit the first electronic device that's going to be modifying the output. Well, on each of these panels, you've connected a microinverter. So the only place that applies is really in the MC4 wire that's going between the panel and the microinverter. So now the microinverter is going to balance or basically clean out any of that variability in the solar output. So it's coming out steady state. So the variability disappears with a microinverter at the point of the microinverter. Same thing with a power optimizer. It's really right at the panel. So you can ignore that second 1.25. The only time you need to put that in is if you're then running without an electronic device that modifies the output from the panel to, say, a combiner box like we did in last week's example. So the fact that on rooftops now, because of rapid shutdown, pretty much the NEC says you've got to put some sort of electronic device attached to the panel for rapid shutdown provisions. And rapid shutdown, hopefully people have read through that, but it basically says when I disconnect from the grid, the panel has to disconnect at the array. All right, since I've touched on rapid shutdown, let me just try and show what I'm talking about. Let's say I've got a solar array up here on the roof. A typical way we used to install these things is, let's say that I'm going to have my combiner box or my junction box under the array. I'm going to penetrate into the attic, and then I'm going to run it over in the attic here to the side of the house. I'm going to come out the side of the house, and I'm going to go down here to a DC disconnect. Then I'm going to go into the basement. So let's say this is the first floor here. Kind of put the DC disconnect too low. I'm going to go into the basement, and I'm going to connect in to my inverter. Again, this used to be a very standard way of designing a system. Then from the inverter, you're going to come out to the side of the house and put in and connect to your AC disconnect. And then from the AC disconnect, you're going to go back down into the basement and hook into your service panel. So it was kind of kludgy how all of this stuff worked. Now, what we're getting to here is the house suddenly catches on fire. So there are flames shooting out of the roof, and the firemen show up. First thing they do is they find the electric meter and they pull the meter. Well, the meter typically will say, that they do that because they don't want live electricity in the house while they're trying to put out the fire. But on the meter, there should be a label that says, hey guys, there's another alternative source of power here at the site. They look around. That's why your AC disconnect has to be located within 10 feet of the meter. They see this AC disconnect. It says solar system main shutoff. They turn off the AC disconnect. Question you now ask yourself is, where does the system shut down? Let's assume it's bright sunlight. It's the middle of the day. Well, the anti-islanding shutoff is in the inverter. So it turns off at the inverter. Well, the problem is the line that goes from the array down the side of the house, through the DC disconnect, into the basement to the inverter, that's still live. That's live power. That could be 600 volts. And so a fireman climbs up onto the roof, starts cutting with their chainsaw through the roof to vent the solar array, and they die. They cut right through a 600 volt live wire, even though they've pulled the meter and they've disconnected the AC disconnect. So the NEC in 2014 started the process of saying, you know what, when you turn off this AC disconnect, the power has to stop at the array, basically. Has to turn off at the array. Well, at the time, everybody in the industry was going, well, how do we do that? And the NEC said, we don't care. Just do it. They don't care how much things cost. They don't care if it's even technically possible. So that led to the widespread adoption of power optimizers and microinverters. Because if you put a microinverter up here on the roof, well, that's where it shuts off, right at the panel. So you've met the rapid shutdown provision. If you put an optimizer in there, well, they put the rapid shutdown in the optimizer. So basically now, every single rooftop system has to have an electronic device on each panel that shuts it off when it loses sight of the grid. That's the way it's been designed. Now, problematically, we're beginning to have systems that are designed to operate when the grid goes down, AC coupled and DC coupled systems. So you might have a battery backup thing. So the idea is, if you disconnect from the grid, the system should still be functioning. That can be problematic for your first responders. So now you're probably, with a system like that, going to have another disconnect switch out here, which they call usually the rapid shutdown initiator. And when you disconnect that, you're turned off all your batteries. You've turned off the microinverters if they're if they work without batteries, like the IQ8s. So everything gets shut off. So now it's basically when the first responder runs in, they pull the meter, they turn off the AC disconnect, they turn off the rapid shutdown. They've got 3 switches now to turn off. Well, that's still within the 6 handle rule. What you want is there not to be more than 6 handles that they have to turn off in order to disconnect power from the grid. Anybody confused by all of that? You can be confused. You can just ask. I'm used to confusing people. All right. Okay, so we're back to this design. Okay, so how does this work? Well, we don't have to do the second one. That was a long way of answering that. So the wires are going to be 2187. So the proprietary wire is super expensive. So typically what you'll do is it comes in little pigtails. There'll be some sort of junction box up here under the array, or if it's a ground mounted system, it'll be under on the pier under the array. So it'll be under the array somewhere. And this is just a transition point where you go from the circuit. This is referred to as a branch circuit. And now you're going to move to a different kind of wire because you don't want to keep paying for that kind of wire that comes in the branch proprietary wire. Now, my recommendation, you could go with 12 gauge wire, but I always recommend don't use anything smaller than 10 gauge for a variety of reasons. But, you know, if let's say we had a long distance to go, we might find voltage drop is starting to impact our production adversely. So we'd want to go with bigger wire anyway. But there are just a lot of reasons where bigger wire is better. And the difference in cost between 12 gauge and 10 gauge is just not that significant. So let's transition to 10 AWG. All right, from here, from that junction box, we are now going to go somewhere probably outside to a combiner box. And if this is an N-phase system, N-phase has a proprietary combiner box. And this combiner box can accept up to 4 20 amp branch circuits. So if you wanted to add another part of your array later, you know, if you, let's say you wanted to expand your system, you got an electric car and you want to put it over your garage, you could put another branch circuit and then just simply come down and connect to this same piece of equipment. And from that point on, everything remains the same. So it's not going to be that big of a project to increase the size of this system in the future. All right, here is also where the communication device is. So the communication device is built into the combiner box, and it will hook into your local Wi-Fi, and it will begin to monitor your system that way. You can also hook in load management systems. They have a whole bunch of different proprietary things. From here, you would typically then go to an AC disconnect. And then from that AC disconnect, you go into your service panel inside the house. And here we are. Now, this goes to the meter. I always draw the meter somewhere away from the AC, but they're located near each other. So that's the meter. Then it goes off to the grid. All right. So Albert, since we're still designing your system, you have 200 amp service, I assume?
I think so. It's a newer house, so yeah.
Yeah. So it's probably 200 amp. And I'm assuming, let's just for the sake of it, say that you've got a 200 amp rated panel. Well, then what's the maximum we can come in here with a breaker?
240?
Well, we can come in with 40 amps.
All right.
It's going to be 240 volts. But it's the 120% rule.
Right.
So 40 amps. Well, with your system's only generating 21.87 amps for that. So we would have in here, well, that system is only going to come into a 20 amp breaker. So from that 20 amp breaker, so you can see that 17.5 amps, even though the wire is sized to handle more, we're still apparently just going to go with the 20 amp. So it may be that anyway, I don't want to back up. I'd have to look, but we're good. So I come in with 20 amps. We could have a 30 amp AC disconnect if we wanted. But if you want to expand in the future, we want to make sure that the wire size is adequate, right? To do your expansion in the future. So what I would recommend, you're going to have 10 gauge wire flowing from here to here, but from the combiner box to your AC disconnect, I'd size your wire to handle the maximum output from this unit, which would be 80 amps. You're only talking about very short distances. So at that point, 80 amps, if you look up in your table, what are we talking about? Is it like 4 gauge or 2 gauge? It's on page 104.
I have to leave that to somebody else. My whole screen's showing your screen.
Okay, somebody with a paper book. Yeah.
Yeah.
All right. So anyway, let's assume, so you're going to size the wire and you're going to base it on 80 amps of capacity. And then your AC disconnect, you'll then probably want to do a 100 amp AC disconnect just so it can handle the maximum. From here, you're going to go with an 80 amp wire going in. But at the moment, what size breaker are you going to use? Well, 20 amp. Because we're only using one of these strings or one of these branch circuits. So we'll come in with 20 amps. We could expand it to 40 amps by doubling this if we needed to. But the reality is if we needed to do more than that, well, this panel in this way wouldn't handle it. We'd have to then go to a supply side connection. And the supply side connection basically says, instead of connecting in here to your service panel, let's take your AC and let's connect in anywhere between the meter and your main disconnect. So this is the point of connection. Now, certain things are required when you do that. The minimum ampacity for this wire has to be 60 amps, but we're going to be basing it on 80. The minimum for the AC disconnect has to be 60 amps, but we're going up to 100, so we're fine. And then we get into the 10-foot tap rule and the 25-foot tap rule. I don't want to get into that at the moment, but this is another option somewhere between there and there. You're not going to need that. Your system will never be that big. You don't have enough roof space for it to be that big. So, so this would be your microinverter system. Albert, does that make sense to you?
It does. I couldn't do it myself, but it makes sense.
Yes, you could. By the end of this class, you could do it yourself. The only thing you're going to lack is confidence and maybe the ability to climb around on your roof. I don't know about that, but that's why you hire teenagers. They're expendable. They're expendable. So, all right. So this is kind of how you would do that system with a microinverter type system.
And do any of those programs tell you what the cost of the materials would be, given that we know?
Some of them will, like the Iron Ridge system. When you design using the Iron Ridge system, it'll give you a bill of goods and it will give you a retail price. That retail price is usually higher than you can get from a distributor. So that's kind of worst case scenario. The rest of them, you kind of just have to price them individually. You can go into a distributor like if I wanted to go in and do the Enphase ensemble system, well, they used to call it the ensemble. I don't know what they call it now. They keep changing their names, but a little bit different system here. With yours, let's say, and this is the system I'm putting in here at our office, and I want to now be able to have battery backup.
Mhm.
Now or in the future, right? Well, let's say I decide to go now. The way that I would have to change this is now I would have to put in what they're referring to as the smart switch. And this is a piece of equipment from Enphase. It costs about $2,000, $2,500, something like that. We'll get rid of that connection. We'll come in from here and it connects into the smart switch. So it doesn't connect in directly there. Now from here, from the utility, we connect into the smart switch. So I get rid of this connection. So I'm disconnecting my main there. Obviously, this is going to require a electrician because the service has to be disconnected. I'm going to get rid of some of this. Okay, so now from the smart switch, we're going to go into the main here. From here, we're going to go to, there will be a disconnect. The rapid shutdown initiator. Now, this, oh, I didn't want to get rid of that, but since I have it. All right, so this is your service panel. All right, so now just to see what's going on here, another thing that you can hook in here is your battery bank. Or what I'm going to be hooking in is my EV charger with my the battery on my car. So rather than a battery bank, I'm going to use the battery from the EV. Now within here is your auto disconnect. So we're coming in with our solar array. That's one source of power. We're coming in from the grid, another source of power. We're coming in with an EV charger or a battery bank, or you can put a generator and connect that in here if you want. So that's going to be another source of power, gets connected into this smart switch. And then it manages all of the load. It manages everything. So if the grid goes down, it's going to disconnect automatically the point of connection from the grid. And now it's going to function to your main from your battery, from your solar array, from your EV. You'll be in standalone mode. When the grid reestablishes itself, it will then reestablish the connection to the grid so that you don't island back out to the grid, sending power out there when the grid is down. You have to have a rapid shutdown initiator because if the first responders come, you've got to be able to turn off all of these power sources and make your home dead. Now your local municipal code enforcement people may require an AC disconnect out here next to your meter just because they've always been told that's what you need. If that's the case, you know, you'll put one in, but it really is not necessary. And the way I would put it in, rather than me draw it over there, is I would just put the AC disconnect between the combiner box and the smart switch. That's where they're going to want to see it. It's not going to do anything more than this rapid shutdown initiator will do, but they may require that you have it there just because they're used to seeing them there. So this is kind of where we're moving towards in the world of residential. Little bit more complicated, lots of load management. Fortunately, it's handled all in this one unit. That one unit is warranted for 10 years. So, it's quite a nice thing. But what I'm doing with mine is I'm not quite ready for this yet. So you can wire it, but just make sure you leave room and extra cable and things to hook in a smart switch if you need it. Because you can do the same thing here now by simply not hooking into the smart switch, but hooking in over here for that. Not hooking into the smart switch there, but hooking into the panel like just another double pole breaker. And then basically that's it. All the rest of this can happen later. So what we've decided with our design is we're just going to put a cable tray underneath all of these pieces of equipment that run from the smart switch to the combiner box to the service panel. And then we're just going to put a couple of loops of wire in there, when we run our cable, just to give us a little bit of flexibility to expand things without having to make another connection. Now I'm sure I've confused some people. So
Is Enphase the only company that makes the smart switch kind of technology?
No, they're all moving towards that, and we're seeing them as DC coupled or AC coupled systems. Solar Edge, they have a system. They call it their Store Edge system. That's the other residential one that's out there. That's a DC coupled system, and their inverter acts like the smart switch. So you just simply hook into the inverter, and the inverter is the place where you would connect in your EV charger. You would connect in to the utility through that inverter. So it's a much simpler system because it's still DC to DC. So all of the work handles within the inverter, and the hooking up in these inverters, I'm making it sound more complicated than it is. It's really just connection points, and it says hook your battery in here, positive and negative. Hook your EV charger in here, positive and negative, or two hots and a neutral. It's really pretty straightforward. Then the question is, you just hope it all works, when you're done. Usually you forgot to do something stupid and the system doesn't work, and you spend 6 hours troubleshooting it or whatever. So, all right. I know that was a long way. Anybody have a question about what we just talked about? We've gone through for about an hour here on that. Next week, I'm going to do another walkthrough. I'll try and design. Maybe I'll design using the Solar Edge system instead of microinverter systems. Give you a sense of that one, and then hopefully we'll be able to do like a full-out commercial type system where we use a string inverter and work through one of those through the problems. But through the week, if you have any questions, just contact me. We'll try and answer those individually. But now you're starting to get into the meat and potatoes of all of this. Hopefully, I haven't checked up on all of you to see if you're in chapter 1 still or not. But, that's, if you're a last minute person, I'm afraid that you're going to have to learn French in a week if you wait until the last week, because you're basically learning a whole new language here. So take your time. Don't hold it off until last week, or you're just going to feel overwhelmed. So anybody have any comments, any questions before we call it a session?
No, sir. Actually, I do have one kind of.
Sure.
Whenever you're talking about the different kinds of like systems with the inverters, do you prefer microinverters?
For small
Or do you prefer,
residential
like, the standard?
systems, yeah, for small residential systems, I do really, yeah, a lot. Any system that's smaller than say 7 or 8 kW, I would just automatically go to microinverter. Just it's ease of installation, ease of use. If you get an electrician, everything's AC, so you don't have to find a specialist, they're just used to it. So Yeah. Now, if you start getting up into a bigger system like a 8 to 12 kW, maybe a optimizer system like SolarEdge would be the option. Then when you get above like 15K, maybe we're talking about string inverters. It's really a commercial system at that point. And but for most residential, I think you'll find that the microinverters is probably the way you're going to want to go. So unless you're right off the bat wanting to do a DC coupled system, in which case maybe financially it makes sense to go with SolarEdge. But one of the things about SolarEdge that we've sort of leaned against is in recent years they've had quality control issues. So their inverters have been failing, and they're under warranty and they'll replace it, but it's a hassle. You know, you've got to get the part, swap it out. You know, it's a hassle. Whereas Enphase has been very reliable. So that's kind of a personal bias for me. So, anybody else have a question? All right. Well, let's call it a day, and we'll see you guys next Tuesday at 1 o'clock. All right. Take care.